Hi friends, myself Narale, working as an assistant professor. Today we will discuss analytical chemistry paper number 12, unit number 3, colorimetry and spectrophotometry. Outline of this topic contain following points. First point is theory of colorimetry and spectrophotometry. Second, Lambert-Beer's law and deviation from Beer's law. Depends on this topic depends on the Lambert-Beer's law solution medium. Terms used in colorimetry and spectrophotometry. Next point is classification of methods of color measurement or comparison. Photoelectric colorimeter method, single beam photoelectric colorimeter. Spectrophotometer method, single beam direct reading spectrophotometer. Next point is determination of unknown concentration by using concentration absorption plot. And last point is application of colorimeter and spectrophotometry. Introduction of this topic. Colorimetry can be used if the substance to be analyzed is colored, or if it can be made colored by a chemical reaction. Any reaction run addition to reagent, then the reaction carry forward, then substance is product is colored, then this analyzed by colorimetry. Colorimetry is quantitative technique, that is how much amount of substance in the reaction, which make use of the intensity in color of a solution is directly related to concentration of the colored species in it. In colorimetry analysis, the intensity of the color of unknown solution is compared with the intensity of color of standard solution of same substance, and concentration of the unknown solution is determined. A simple instrument used for the colorimetric analysis is called a colorimeter or color comparator. In colorimetry, this visualized by two method, ultraviolet and visible range. Range of the wavelength is ultraviolet 185 to 400 nanometer and visible range is 400 to 760 nanometer, and then again infrared is 0.76 to 15 micrometer. Theory of colorimetry and spectrophotometry. When light is incident upon a homogeneous medium, a part of the incident light is reflected, a part is absorbed by the medium, and the remainder is allowed to transmit as a such. In these 3 points, when light is passed through substance, then the one is reflected, one is absorbed, and one is transmitted. If I0 denotes the incident light, IT is the reflected light, and IA the absorbed light, and the light then we can write I0, that is I0 is a incident light plus is equal to IA means absorbed light, IT is the transmitted light, plus I is reflected light. If comparison cell is used, the value of IR reflected light, which is very small amount, that is 4%, can be eliminated for air glass interfaces. Under this condition, the previous equation can be written as I0 is equal to IA plus IT. The two separate laws governing absorptions are generally known as Lambert's law and Beer's law. Lambert's law states that when beam of monochromatic radiation passes through homogeneous absorbing medium, then rate of decrease of intensity of the radiation with thickness of absorbing medium is directly proportional to the intensity of the incident radiation. That is, minus di upon dt is equal to ki. Ki is the absorption, I is the intensity of the radiation after passing the thickness t of the medium, and di is infinitesimally small decrease in intensity of the radiation after passing through the substance. Next law is, this depend on the Beer's law, that is Beer's-Lambert's law. Lambert's law only depends on the absorption medium, but when in Lambert's law, when a beam of monochromatic light passes through a colored solution, the rate of decrease of intensity of the light with the thickness colored solution is directly proportional to intensity of incident light as well as concentration of the solution. That is, minus di upon dt is directly proportional to incident light and concentration of the solutions. That is, minus di upon dt is equal to k into I into C. K is proportionality constant, that is molar absorption coefficients, depends on the y lambda of the light and the nature of the substance. This diagram, when monochromatic beam of light pass through, that is I0 pass through the solution, then the transmitted light, after absorption the light is transmitted, that is directly proportional to the intensity of incident light with thickness. Where from this equation, then integration, final equation of Beer's law is, therefore IT is equal to I0 10 raised to minus epsilon Ct, where epsilon is equal to 0.4343 and K is equal to molar extinction coefficient of absorbing solution. Above equation is the mathematical expression of Beer's law. According to Beer's law, when from this equation, when monochromatic light passes through the colored solution, the amount of light transmitted decreases exponentially with increase in concentration of the colored substance and thickness of the solutions. In this topic, important terms used in colorimetry and spectrophotometry. Transmittance or transmission symbol is T. It is defined as the fraction of incident light through the thickness T of the medium. That is, T is equal to IT upon I0. Opacity, the reciprocal of transmittance is called as opacity. That is, opacity is equal to 1 upon T. That is equal to I0 upon IT. That is reciprocal of the transmittance. Next term is optical density D or absorptions A. Logarithm of opacity is called as a optical density of absorptions. D is equal to log 10 I0 upon IT, or second as T is equal to IT upon I0 D is equal to log base 10 to 1 upon T. Hence, optical density is the logarithm of reciprocal of the transmittance. Next terms, molar extension coefficient, that is epsilon symbol. We have from the Beer's law, IT upon I0 is equal to 10 raised to epsilon Ct. Therefore, I0 upon IT is equal to 10 raised to epsilon Ct. Therefore, log base 10 to I0 upon IT is equal to epsilon Ct. Therefore, D is equal to epsilon Ct. Therefore, log base 10 to I0 upon IT is equal to D. If C is 1 mole per dm cube and T is equal to 1 cm, then equation becomes D is equal to epsilon. Hence, molar extension coefficient epsilon can be defined as the optical density D when layer of solution is 1 cm thick and the concentration of the solution is 1 molar dm cube. Last term, specific extension coefficient ES, it is the optical density per unit path length and unit concentrations. Applications of Beer's law. Example of Beer's law: consider two solutions of colored substances with concentrations C1 and C2. These solutions are kept in the instrument in cuvette in which the thickness of the layer can be altered and measured easily. This instrument also allows comparison of the transmitted light when the two layers have the same color, thickness we have, intensity we have. IT1 is equal to IT2, that is the thickness of the solution. According to Beer's law, therefore I0 10 raised to minus epsilon C1 T1 is equal to I0 10 raised to epsilon C2 T2. Therefore, C1 C2 is equal to C2 T2. Here from this equation, T1 and T2 are the length of the column of solution with concentration C1 and C2 respectively. When the system is optically balanced, colorimeter can be used. From this equation, to determine an unknown concentration C2 of the colored solution by comparison with the solution of unknown concentration C1. To verify Beer's law by changing C1 and C2, if law is obeyed, then Tc is equal to constant. Deviation from Beer's law. Deviation from Beer's law may occur under following conditions. First, when colored solute ionizes or associate in solution or form complexes. Second deviation, when large amount of this solute present in solution, less amount of solute is used, then the deviation is formed. Linearly formed in following graph, concentration versus absorption, the linearity form, then the deviation is large or excess amount is used, then the positive deviation and negative deviation is in Beer's law. When temperature is not kept constant, then deviation also form. When after some time color of colored compound increases or decreases, any reaction completed, these compounds form the color, then the intensity of light is decreases to form the deviation of these reactions. When monochromatic light is not used in the deviation light. Thank you for listening or watching.